Okay, so do you have any questions to start with? So if you remember, the last thing we did on Monday was we were talking about the operators and how we represent the operators. We talked about the matrix representation, and also we said that if in the Hilbert space we use the eigenkets of an operator as our basis state, then our operator takes a simple form. Let's say we have these eigenkets of the operator H, which are orthonormal. We can always, we have seen that we can always normalize them, and we can choose them to be orthogonal to each other, even if there is degeneracy. If there is no degeneracy, kets corresponding to different eigenstates are automatically orthogonal. But if there is degeneracy, then still we can choose our basis as an orthogonal set. And then we said that in this basis, this operator has a quite simple representation. In particular, we applied it to our Stern-Gerlach experiment, and that is the Z component of the spin. And if you remember, in the Stern-Gerlach experiment, basically the silver atoms, they are split into two. One of them we call the plus, and the other one we call them the minus, and they turn out to have the Z component of the spin plus h power over 2 and the Z component of spin minus h power over 2, so that the operator corresponding to Sz is simply h power over 2 plus plus plus plus minus h power over 2 minus minus. And we also had seen that we can show this operator in matrix form in this two-dimensional Hilbert space as h power over 2 minus h power over 2 and 0 everywhere else. So it's a diagonal matrix already. Well, on Monday we didn't talk about the x component of spin and the y component of spin. So today we will be basically dealing with the x and the y components of spin. Now, of course, first thing we have to do is we have to somehow identify the Sx plus and Sx minus states. This is for the x component of spin, and Sy plus Sy minus components. And again, Stern-Gerlach experiment told us that, I mean, we cannot really say that a state is Sx plus and Sz plus. We can only specify one of them. Which led us to this two-dimensional Hilbert space. So we will be describing our states in terms of this Z plus and Z minus states. So if these two states are enough to describe our system, whatever our system is, Sx plus, Sx minus, Sy plus, Sy minus states we should be able to also express them in terms of these plus and minus states. So this Sx plus will be equal to, let's say, of A plus plus B minus, and Sx minus will be some C plus plus D minus state. So of course, one thing is we also need to give some interpretation to these coefficients A's and B's. And in general, if we have a state, let's say gamma, written as a superposition of the states alpha I with coefficients, let's say Ci. Now, one thing we know is we would like to work with states that are normalized to 1. So all gamma gamma which is equal to sum over I and j, Ci, Cj star, alpha j, alpha I. No, that is gamma gamma. I'm looking at gamma gamma. That should be 1. Where? On the right-hand side, it is alpha. You see, gamma is our arbitrary state describing my system, whatever my system is. I know that my cat, I can write it in terms of the cats in my basis set, which are the alpha I. So this is always true. Now, of course, one problem is, okay, fine, this is a mathematical representation of my state, but how do I interpret this? Well, the plus state that we were talking in the Stern-Gerlach experiment was, well, it was kind of easy experiment, already gives us how we should interpret it. The plus state is the state that is deflected upwards. And the minus state is the state that is deflected downwards. But in general, we can talk about any linear combination of plus and minus states with certain coefficients. So how do we interpret those states? One thing is, we will say that gamma yes. Okay, so what we are actually doing here is, okay, one thing is, what is this Hilbert space? The problem we were facing with, okay, in classical mechanics, for example, we talk about when we want to describe our state, we talk about the velocities of the particles, the position of the particles, the x, y, z components of the particles. We can specify all of them. So when we have, for example, the silver atom, okay, that is our Stern-Gerlach example, we are saying that, okay, the silver, if we send the silver atom through a non-uniform magnetic field, it will interact with this non-uniform magnetic field. It will feel a force that will depend on the orientation of the spin. In classical physics, this orientation of spin can be any direction. So if we just send a bunch of silver atoms, we know that these silver atoms will be deflected in all directions with a maximum upward deflection, some maximum downward deflection, but depending on the orientation of the spin, it can be deflected in any range in between. Okay, that is what we expected in classical physics, basically because we could talk about some arbitrary values of the x component, y component, and the z components of spin. Okay, this is classical physics. But it didn't match the observation. Our observation was that the silver atoms were sent only in two directions, either upward or downward. So, and furthermore, by doing this sequential Stern-Gerlach experiments, what we observe is that we cannot really talk about the x and the y deflections at the same time. So if you remember, what we did was, okay, we sent our silver atoms through a Stern-Gerlach experiment that in the z direction. We only picked the atoms in the z direction. So in principle, they should always be deflected. In classical thinking, if nothing changes that property, they should all be deflected in the z direction, all those silver atoms, because they have a definite z component of spin. So that is classical thinking. Then we send it through a Stern-Gerlach experiment in the y direction, let's say. Okay, so the first Stern-Gerlach experiment splitted my silver atoms according to their z component. The second Stern-Gerlach experiment separated them in terms of their y components. So if classical physics, classical description was correct, we should be able to talk about the silver atoms that will be deflected in the plus z direction and also in the plus x direction, let's say. But what we did, our third experiment, is we send them through the Stern-Gerlach experiment in the z direction. Then in the x direction, we always show the plus components. Then we send it again in the z direction. So what we observed was this Stern-Gerlach experiment in the x direction kind of completely erased the information that we had chosen the silver atoms that are deflected in the plus z direction in a Stern-Gerlach experiment aligned in the z direction. So it completely erased it. Now that description in terms of the x, y, and z components of the spin kind of failed in these Stern-Gerlach experiments. And then we looked at this analogy with light. In light, we are talking about the polarization vector. So if assuming that the photon is moving in the z direction, then the polarization of the photon is in the xy plane, perpendicular to its propagation direction. And if you use filters for light, you get exactly the same description, exactly the same observations that we observe in sequential Stern-Gerlach experiments. So we can choose a filter that chooses the photons in the x direction. Then if we send another filter that is polar, if we send this photon through another filter that picks up only the y component, nothing passes through. But if we send it first through the x, then through some other filter that makes an angle that's not 90 degrees with the initial filter, and then we send it through this filter in the y direction, then we see that there's something that passes through. That is exactly analogous to our observation in our sequential Stern-Gerlach experiments. So this is our mathematical description. So we said that, okay, just like for the photon, we use polarization, a two-dimensional vector, to describe the system. For the silver atoms, I will also use something similar to polarization. Later on, we call that the spin of the silver atom. So rather than using the x, y, and z components of the spin, I will say that I will describe this spin as a superposition of two states. Just like in the case of the photon, we have the polarization in the x direction, polarization in the y direction. Any polarization we can write as the superposition of these two. So for the silver atom, I'm also making the same analogy. I will say that the spin state of my system, whatever the spin state is, I will write it as the superposition of two things. For the time being, let's just call them things. They're not vectors in our real space. They're just objects. We invent some abstract objects. But we will be talking about their sum. We will be multiplying them by numbers. We will be just considering these sums. Now the question is, how should we interpret these sums? Okay, we write them, but if you have things that you can multiply with numbers and add them, mathematicians call it a vector space. So in that sense, it's a vector space. It is not the real space. I mean, we are not talking about vectors like momentum, or we are not talking about vectors like position. These are some other objects. They are not related with our real space. They might be, but they don't need to be. These are things that we can add, multiply with numbers. We can talk about their inner products, etc. In that sense, this is a vector. Then the problem is, how do we interpret these vectors? You see, what we do in classical physics. If you think about what we do in classical physics, we first measure some numbers that we call the position and the velocity, let's say. Then with these numbers, we have the laws of nature, which tells us how these mathematical objects change in time. So we start with these numbers, we study how they change in time, and then we obtain some new numbers. But they are just numbers. When I say that a particle is at the point for a given coordinate axis at the 1.2 meters in the x direction, well, you see, this is not the position of my object. This is a mathematical representation of the position of my object. My object is over there. That is not 1.2 meters. But I show it mathematically as this using these symbols. So in physics in general, what we do is we look at nature, we construct a mathematical representation, we manipulate that mathematical representation, and then we interpret our results in terms of nature. So that is always the flow. We look at nature, make a mathematical model, manipulate that mathematical model, and then interpret our final mathematical model. So that's basically what we are doing when you look at r is equal to 1.2 meters in the x-hat direction. Well, you are not realizing it most of the time. It's so automatical for us. But actually we are kind of, this is not the position. This is a symbol or a series of symbols using which we can find the particle. Just like that, we saw that this description, this way of making a mathematical model and manipulating those things, don't really describe the nature properly, at least in certain cases. The silver atoms passing through a Stern-Gerlach experiment. We couldn't describe it in that way. So now we are just constructing a different mathematical model. So that's basically what we are doing now. And of course, finally, we have to be able to, we have to first show our observation in terms of nature as a mathematical set of symbols. We should be able to know how we manipulate those mathematical symbols. So that's what we have done up to now. So we have been talking about these kets and how we can multiply them, sum them, how we can show them as matrices, if you like. Matrices are some things that are most of the time more familiar to us. How we can show as matrices. So once we can show them as matrices, we can just use all the machinery of matrix algebra. So that's the nice thing about showing in terms of matrices. But the part that we are still missing is how do we interpret those things once somebody gives me some answer, some symbol, let's say, like this one, how do I interpret that? So that is what we are starting today, kind of. And this, our mathematical representation, the current mathematical representation is what mathematicians call a Hilbert space. We will be dealing with vectors in Hilbert space. They're not vectors like the position vector or the momentum vector. We call them vectors basically because we can multiply them with numbers, we can sum them. That is why we are calling them vectors. Now, of course, the interpreting thing. Okay, we said that we can multiply them with numbers. So I have this ket or this vector in Hilbert space. I can construct this other ket in Hilbert space. C being some complex number. And C is not equal to 0. So I have these two kets. Well, the way we will interpret these two states is that they correspond to the same physical system. Well, if we can multiply a ket by an arbitrary number, and they still correspond to the same system, I can use my freedom to choose any one of, you see, again, back to our analogy in real space. You have this vector. If you multiply this vector by 0.5, you get this vector. If you multiply by 2, you get the vectors pointing in the same direction, but twice as long. If you multiply it by -1, you get this other vector pointing in the other direction. So if you just multiply a given vector by some arbitrary number, the tip of your vector basically traces a line. So basically what this states are, what this command, this expression states is that, well, the states do not actually correspond to one vector, but they correspond to some ray, some line in our Hilbert space. We usually, it doesn't really matter so much because since all of these vectors correspond to the same state, to represent this ray, we just pick one of them. And that one of them, we pick using the condition that it should be, its magnitude should be 1. You don't have to choose it to be 1, but it will make our life easier. Now, if we have an arbitrary state written in this form, then these coefficients Ci, they need to satisfy some condition because so that our state gamma is normalized to 1. Gamma gamma. This is equal to sum over I, Ci star alpha I. This is the bra corresponding to the ket gamma. Multiply it with J, Cj, alpha j. Well, if you just combine the summations, Ci star Cj, alpha I, alpha j, our basis, unless stated otherwise, we will always exclusively work with orthonormal basis. So this is Kronecker delta ij. Now if I sum over the j, it just tells me that this Kronecker delta tells me only the j is equal to I term survives. So this is I Ci squared. So this is one condition that our coefficients should satisfy. Well, if you are familiar with probability theory, the sum of all the possible outcomes, the probabilities of all possible outcomes should be 1. This just looks like it. So you see, if you have this state, when I make a measurement on it, I can observe it in the alpha 1 state. I can measure it in the alpha 2 state. I can measure it in alpha 3 state. If you just prepare identical systems having the same gamma, some of them I will measure in C1 state. Some of them, if I make a measurement, I will measure in C2 state, some alpha 2 state. Some of them I will measure in alpha 3 state, etc. There will be a distribution. And this Ci, well, since I'm making many measurements with different outcomes, well, I can talk about the probability of outcomes. And it turns out that the Ci squared is the probability that a measurement of h, whatever my observable is, well, I'm using the h not to denote the Hamiltonian, but mainly it's a Hermitian operator. That a measurement of h will yield the value of I. Now, what's the derivation? No, there's no derivation. This is just one of the interpretations of quantum mechanics. So the problem is, what do you do with superposition states? I mean, if you have pure eigenstates, then it's kind of easy to interpret them. We know what they are. But quantum mechanics allows us to talk about superpositions. So the problem is, what do they mean? And this is the Copenhagen interpretation of superpositions. For example, we will be talking about states of this form. Well, the Copenhagen interpretation tells me that if you make many measurements on identical states, some of them will turn out to be in the SZ plus, some of them will turn out to be in the SZ minus. And the probability that, if you just pick up one measurement, the probability that it will be a plus state is just absolute value of a squared. The probability of SZ minus will be just absolute value of b squared. This is not the only interpretation, but this is the, let's say, the widely accepted interpretation. Now, the problem is, if you make many measurements, if you have systems prepared in identical ways, and you make thousands of measurements, millions of measurements, then you can talk about the probabilities, and the probabilities, whatever your interpretation is, corresponds to a squared being the probability of plus, b squared being the probability of minus. Now, the interpretations usually differ when one wants to talk about a single system. So what happens to a single system when you make a measurement? Well, you see, for a single measurement, you cannot actually talk about a probability neither. I mean, measurement is either this one or this one. And what happens to our state after the measurement? That is Copenhagen interpretation. Not all interpretations accept this collapse conjecture, let's say. So there are many worlds interpretation, there's the coherence, etc. But we will stick with the Copenhagen interpretation of collapse. So basically what that means is, suppose you have this system, gamma, A, let's say alpha 1, A1 plus A2, alpha 2. Then you make a measurement. And the outcome of the measurement is measurement of H. And the outcome is alpha 1. So we have our observable, which we call, there is a corresponding operator to our observable H. And the possible values that we can observe will be the eigenvalues of H. And we make a measurement of this observable. And we measure that this observable has the value alpha 1. After the measurement, the state, this is before, the state of my system is alpha 1. A1 is lost, A2 is lost, alpha 2 is lost. So this is what we call the collapse of the wave function. Yes, exactly. Well, that is what we call about measurement. I mean, that's something you expect about a measurement. If you make two successive measurements of the same thing right after one another, you would expect to have the same outcome. So that's one of the motivations of this collapse interpretation also.
Süperpozisyon dediğim olay şöyle bir şey oluyor. Elektron birçok noktada bulunabiliyor. Ve o noktalar sadece bir equation'a göstersek spesifik bir yer göstermiş olacağız. Şuradan şuraya. Ama elektron öyle bir özelliği olmadığı için birçok yerde bulunabiliyor. O aslında bulunmadığı için bir süperpozisyon kullanıyoruz.
Ya aslında yani gördüğümüz şey şununla tutarlı gibi görünüyor. Elektronun konumundan bahsedemiyorsun bile. Elektron aynı anda hem her yerde hem hiçbir yerde. Tabii şimdi sen ölçüm yaptığında bir değer ölçüyorsun. Şimdi bunu nasıl yorumlayacağız? Şu anki işte dediğim Kopenhag yorumu diyor ki işte kuantum mekaniksel sistemler bir süperpozisyon halinde. Şimdi bu süperpozisyon halinde işte farklı konumlarda olma olasılıkları var. Ama ölçtüğüm ana kadar bunun belli bir konumu yok. Ölçtüğüm zaman bu belli bir konum kazanıyor. Niye? Collapse'den dolayı. Bir ölçüm yaptım, bir konum buldum. Ondan sonra hemen bir ölçüm yaptığımda yine aynı konumda göreceğim elektronu. Başka bir yerde görmeyeceğim.
Peki biz o elektron equation'ı nasıl çıkarıyoruz? O equation, yani bir elektronun hiçbir yerde olmadığı ve her yerde olmadığının equation'ı nasıl çıkartıyoruz?
Geleceğiz yavaş yavaş. Yani daha specific description'lara geleceğiz. Yani şu anda elimizdeki en basit örnek mesela spin durumları. İki farklı durumda olabileceğini biliyorduk. Mesela şunu nasıl bulacağız? Yani eigenketlerimiz dedik ki S-Z'in eigenketleri olsun. Onu zaten biliyoruz. Şimdi bir sonraki problem tam Z'i seçtik. X'i nasıl tanımlayacağız? X'i nasıl yazacağız? Bir ona bakalım şimdi. Ondan sonra daha komplike işte konum gibi sonsuz tane değer alabilen durumlara da zaman içinde geleceğiz.
Konumdan bahsederken klasik matematiğin bir konumdan bahsediyoruz.
Bildiğim tek konu mu?
Yani ben mesela şu lambanın yerini söylerken işte bir rakamlar verebiliyorum.
Tabii.
Peki biraz önce söylediğimiz mesela atomda elektronun yerine o ölçüm yaptığımızda, kolaps ettiğimizde yine o tarz bir sonuç mu? Peki.
Evet. Yani sonuçta konum dediğim şey aslında parçacığın özelliğinden ziyade uzayın özelliği. Uzaydaki konumlardan bahsedebilirim. Şimdi bir parçacığın konumu dediğim zaman kastettiğimiz şey aslında ben o noktaya gittiğimde parçacığı orada görecek miyim? Şimdi dediğim gibi konum uzayın bir özelliği. O konumdan bahsedebilirim. Oraya gittiğimde parçacığımı görecek miyim ben? Yani bunun için belli olasılıktan bahsedebiliyorum diyor kuantum mekanik. Kesinlikle göreceksin diye bir şey demek çok zor. Ya daha önceden ölçüp orada görmediysem söyleyemem. Yine biz spinimize şimdi geri bir dönelim. Two state. That's the easier part, easier system we have. So what do we know? We are trying to write the Sx plus and Sx minus states. Again, let's go back to Stern-Gerlach experiments. This is my Stern-Gerlach experiment, which has a magnetic moment in the x direction. So we can then it splits into two. Well, you see, the x direction and the z direction, they don't really have anything different. So if a beam of silver atoms split into two in the z direction, they should also split into two in the x direction, unless we prepare it in a special way. Since initially we are obtaining it from the oven, for them they are completely randomized. They are in thermal equilibrium. They don't have any preferred directions. So this direction, that direction, the other direction, for them are all equivalent. So I take that beam. I send them through a Stern-Gerlach experiment. This time I call that direction the x. I block them, part of it. I take the Sx plus. And then I send it through the Stern-Gerlach experiment in the z direction. Why? Because I'm trying to write all my states in terms of the eigenkets of the Stern-Gerlach experiment in the z direction. That's why I'm sending it through the second experiment. That is my second measurement that tries to determine the components of the Sx plus in the plus z or minus z components. And the observation tells me that they split into two. 50% goes above, 50% goes below. Well, let's see, I know that Sx plus, I wrote it as A plus B minus. A squared is 50%, 1 over 2. B squared is also 50%, 1 over 2. Well, if A squared is, absolute value of A squared is 1 over 2, this tells me that A should be 1 over square root of 2. Do you agree? So, I mean, experiment tells me that the absolute value of A squared should be 1 over 2. So may I conclude that A should be 1 over square root of 2?
Should also be complex.
It can be complex, it can have some phase. So it should, the general form is A should be 1 over square root of 2 times e to the power I alpha being some real number. I mean, the experiment doesn't really tell me what this alpha is. And B squared is, again, 1 over 2, which also tells me that B should be equal to 1 over square root of 2 times some phase whose magnitude is 1. So from experimental observation, I can say that the Sx plus state should be 1 over square root of 2 e to the power I alpha plus 1 over square root of 2 e to the power I beta minus. Or I can also write this as e to power I alpha times 1 over square root of 2 plus e to power I, let me call it delta 1 minus, where I defined delta 1 to be beta minus alpha. So this should be the form of my Sx plus state consistent with my observation. But you see, we said that if we have one kit, and if you multiply that kit with an arbitrary number, it corresponds to exactly the same state. Well, let me just multiply Sx plus by e to power minus I alpha. So if this corresponds to one state, if I multiply this by e to power minus I alpha, still it corresponds to the same state. But that tells me that just cancel this overall factor of e to power I alpha. So the most general ket that corresponds to my Sx plus state is just 1 over square root of 2 plus e to power I delta 1 minus. Again, delta 1 is some number that we don't yet know. Well, I can do the same thing for the Sx minus state. You see, if you go back to our Stern-Gerlach experiment, the Sx minus state, I could have just closed the upper beam and send the lower beam through a Stern-Gerlach experiment aligned in the z direction, and basically my observation would still be the same. Sx minus state will be divided into two equal beams, with 50% going up, 50% going down. And again, everything, all the arguments that we made over here up to this point will be exactly the same. So Sx minus state will be 1 over square root of 2 plus e to power I delta 2 minus. Of course, delta 1 and delta 2, they can be different in general, only using the experimental observation. But then I have one more observation. I know that if I take an Sx plus beam and send it through a Stern-Gerlach experiment, not in the z direction, but only in the x direction. Again, just repeat it again. But this time, I won't see anything in the Sx minus direction. So this should be 0, which basically tells me that a silver atom that is deflected in the plus direction has no probability of being deflected in the same Stern-Gerlach experiment if you repeat it again in the minus direction. Again, our experimental observation. So let's just calculate this inner product. Well, Sx minus bra is 1 over square root of 2 plus e to power minus I delta 2 minus times 1 over square root of 2 plus e to power I delta 1 minus. Now this plus and minus state, by definition they are orthonormal. So if you just take this, multiply it out, 0 should be equal to 1 over 2. Now plus gives me 1 plus e to power I delta 1 minus delta 2, minus is 1, and the cross products, they are all 0. So this should be equal to 0. Well, this basically tells me that this e to power I delta 1 minus delta 2 should be equal to minus 1, or delta 1 minus delta 2, or let me put it this way. E to power I delta 1 should be equal to minus e to the power I delta 2. There's still one unknown phase we have, but at least they are related. So let us sum our results. So we just had found that these two phases appearing in these two states are minus each other. So instead of this one, I can just put minus e to the power I delta 1. Now these are the eigenkets of the Sx operator. Still there is this problem of delta 1. We will handle it next Monday. But up to this unknown delta 1, we know our Sx states. We can write the matrix corresponding to x component of the spin. So if we just write it, the operator corresponding to Sx is nothing but h power over 2 Sx plus Sx plus minus h power over 2 Sx minus Sx minus. We already identified the eigenstates corresponding to this operator Sx. In terms of those eigenstates, this will be the form of our matrix, our operator. I can express these in terms of the states corresponding to Sz plus and Sz minus. Just use the above definitions. This will be h power over 2, 1 over 2, plus e to the power I delta 1 minus, plus e to the power minus I delta 1 minus, plus or minus h power over 2, 1 over 2, plus minus e to the power I delta 1 minus, plus minus e to the power minus I delta 1 minus. I can open up the parentheses. So let's say this is minus h power over 4. I have plus from the first term. And from the second term, I have minus plus. Now they will cancel each other. No, sorry, this is plus h power over 4. Plus h power over 4. Let me look at the plus minus part. Okay, from the first line, the plus minus, I get e with a coefficient e to the power minus I delta 1. And from the second line, plus minus comes with plus e to the power minus I delta 1. The second one is from the second line. Plus h bar over 4, let me look at the minus plus term. Well, from the first line, the minus plus I have with e to the power I delta 1. From the second line, I have it with plus e to the power I delta 1. And then I have h bar over 4 minus term. From the first line, I get with a coefficient 1. From the second line, I get with a coefficient minus 1. So these terms, the first term and the last term, they just cancel. And the Sx operator is h bar over 2 plus minus e to the power minus I delta 1 plus h bar over 2, so this plus minus e to the power I delta 1. Then we can write the matrix corresponding to this operator in our two-dimensional Hilbert space. Well, there is h power over 2, which is common. So this is e to power I delta 1. Here I have a e to power minus I delta 1, 0, 0. Well, the easiest way to check, whether it's the above term that is the I delta 1 or the below term that is I delta 1, just look at some matrix element that is non-zero. So for example, the plus ket, we had shown it as 1, 0. Now Sx acting on this plus ket, if you look at that definition, since plus plus is 0, plus plus is 1, plus minus is 0, it's nothing but h power over 2, e to power I delta 1, 0, 1. But this is nothing but h power over 2, 0, e to power I delta 1, no, sorry, this is plus, this is minus. E to power I delta 1, e to power minus I delta 1. So if you just make the matrix product, the above line will be 0, the below element will be e to power I delta 1, as it should be. So this is our Sx operator. Well, that our ambiguity is kind of, well, it's not a real surprise that we have still some ambiguity. We are talking about x, y, and z directions, but those directions are arbitrary. We fix one axis, the z axis. Let's say this is our z axis. Now we are talking about the x axis. X axis is perpendicular to z axis. But we can choose this as our x-axis, this as our x-axis, this as our x-axis, this as our x-axis. We are just free to choose our x-axis. So the corresponding states is kind of also arbitrary. It depends on how we choose our x-axis. And that arbitrariness is reflected in this value delta 1. And in fact, the value of delta 1 that you choose shouldn't make any difference, because the value of delta 1 that you choose will mainly correspond to whether you choose your x-axis in this direction or in this direction. Physics should be independent of that. So whatever value you choose for delta 1, that is valid. Of course, once you choose your z-axis and x-axis, then you don't have really any freedom in choosing the y-axis. If you are using a right-handed system, which we will use, your y-axis is uniquely determined by your x and the z-axis. So on Monday we will see that we already know our Sx eigenkets. So we will try to look for Sy eigenkets. Once we fix this delta 1, there shouldn't be any ambiguity in the Sy eigenkets. Yes, any last questions? Now, on Monday, when we discuss the Sy eigenkets, I will not go over all of these. Basically, instead of just calling this axis x-axis, we could have just called that axis the y-axis. So nothing would have changed. We would have carried out exactly the same analysis. And we would reach at exactly this relation with a possible different value of delta 1. So that is where we will pick up. So we will start from this and just straight away write the expression for the Sy eigenket. So I suggest you to go over this derivation so that you will be able to follow us.
Burada minus ile x plus arasında 180 derecelik bir phase farkı olduğunu söylüyoruz.
Yes. What we are saying, well, okay, if you say phase difference, then in different contexts that would mean different things. So I would rather state it in this form. If a particle is deflected in a Stern-Gerlach experiment that is aligned in the x direction, in the plus direction, and if we put another identical Stern-Gerlach experiment right after that, it should still be deflected in the plus direction. Otherwise, our measurements, they will be meaningless. If we make one measurement, then a subsequent measurement should yield exactly the same result. So that is what this statement is all about. This is. If we first measure the SX component and see that it is plus, then we measure it again right after the first measurement. The probability that it will be an SX minus should be 0. It should still be SX plus, definitely. So that is what allowed us to relate these phases, delta 1 and delta 2, in the definition. As well, in practice, I mean, we can make successive measurements as small as, I don't know, of the order of 10 to the power minus 10 seconds, for example. We can make such very small measurements separated by such a very small amount. In practice, well, in theory, well, this is just an idealization in a sense. But what does a measurement mean? What does a measurement tell you? So what we expect from a measurement, from a, let's say, a philosophical point of view, is a measurement should tell me something about the state at that instant. Well, we don't expect physics to change discontinuously. We want our measurements, let's say, to change continuously, meaning that if I make two measurements of the same system, of the same property, they might not be instantaneously right after the other, but the difference in my measurement should be very small. For example, if you make a measurement of the position of one particle, you observe it at this point. Right after 1 second, let's say 1 second, you expect your particle to be either exactly at the same point, or it might shift from that point at most by, let's say, speed of light times 1 second. Otherwise, it would have moved faster than the speed of light. Or if I make this measurement of the position, the time difference between two measurements, shorter and shorter, then the difference between the position measurements, two successive position measurements, should get smaller and smaller. That is what we expect. In the ideal limit, that you make one measurement, and right after that one you make your second measurement. That is the ideal limit. Then we want the two measurements to be exactly the same. At least for the time being, there doesn't seem to be any experimental observation that forced us to leave this hope, let's say, this assumption. Maybe one day we will have to get rid of this assumption. This is an assumption, or a definition, an expectation, an interpretation. And for the time being, it seems to be the correct interpretation. And as I said, maybe in 100 years we make some measurements which would force us to leave this assumption. We will. But for the time being, we can stick with it. If we stick with it, the predictions we make, they are consistent with our observations. We will come to the uncertainty next. Well, the uncertainty is basically due to the superposition principle. You see, if you have this state, let's talk about the SX plus state. You don't really know whether its spin in the z direction is plus or minus. If you make many measurements, you will measure as much pluses as minuses. So that is the uncertainty in the Z component of the spin. Now we will define it more precisely on Monday. Okay, so see you on Monday.